So let's look at the following. The function y equals c e to the ket passes through the following points. 0, 6, and 4, 11. We want to find c and k. Excuse me. This question is relatively not terrible when your first point is, why are you having problems? When your first point or one of your points has an x coordinate of 0. It's pretty straightforward in this context. So first, we're going to use that point. So we're going to plug in t equals 0 and y equals 6. And we're going to get 6 equal to c e to the k times 0, which is great because k times 0 is 0, e to the 0 is 1, and we're going to end up getting 6 equal to c times 1, or c equal to 6. And that's typically the case when you are finding your c and your k value. Your c value is your initial value. So if you have some time equal to 0 coordinate here, we know that the c value is going to be whatever that second part is. It's very, very standard. And then to find the k value, we're going to plug in the other data point, t equals 4 and y equals 11. I should say, along with also plugging in c equal to 6, right? Because we're going to use that c equal to 6 to find the k value. So let's see, what do we got here? We've got 11 equal to 6 times e to the k times 4. And now this is a process of solving for k. So whenever you're solving an exponential equation like this, we first need to isolate the e to the whatever part. So we're going to divide both sides by 6. And I typically like to write this as e to the 4 times k. Doesn't really matter, but we usually write constants before. Not that k isn't a constant, but like we like to write number things before we write letter things. It's just the way we do it. And then take the natural log of both sides. So the natural log of 11/6 equals the natural log of e to the 4k. And the whole point of taking the natural log of both sides is the natural log of e to the whatever is just the whatever. So the natural log of 11/6 equals 4k. Finally, k equals 1/4 the natural log of 11/6. Or if you prefer, the natural log of 11/6 over 4. And that's as simple as the k value gets. This question doesn't ask us to, but typically once you have found c and k, then you want to rewrite your model for exponential growth or exponential decay with those values plugged in. So our new model would be, or I should say our model where we've solved for c and k is going to be y equal to 6 e to the natural log of 11/6 over 4 times t. There are other ways of writing this, but this is pretty standard. So this is kind of, in my opinion, the quote unquote easier version of this question. Let's look at a slightly harder version where the 2 points we're given are not so nice. Also, for those of you on Zoom, please do feel free to chime in with questions or type something in the chat. I think, oops, I meant to do this thing and then I forgot to do it. The chat is only to, well, I thought I was, why don't you want to click? Oh, I see, yeah, cool. You should only be able to send me a chat, so no one else will see your question if you have a question. So let's look at this next one. Let's say we're given, again, y equals c e to the kt, and now it's passing through the points. How exciting. Let's say we've got 2, 7 and 6, 13. I've probably made numbers that are going to turn out to be gross, such as life. Not all the numbers are always nice. So here we're going to do the same thing. We're going to plug in the t and y values, And then we're going to try and solve for C and K. But the less nice part here is that we don't just get C automatically. So plugging in the first ones, if I plug in 2, 7, I'm going to get 7 equal to C e to the K times 2. And it's not really great. I can't just figure out C or K from this. So I'm going to solve for one of them. And typically, if I have to choose, I'm going to solve for C here because it's just easier. So isolating C, I get 7 divided by e to the 2k equals C. And then we're going to do the same thing for the second coordinate. If we do that, we're going to get 13 equal to C e to the k times 6. Or isolating C, 13 divided by e to the 6k equals C. And then we can set those equal to each other and solve for k. So setting those equal to each other, I have 7 over e to the 2k equal to 13 over e to the 6k. My first thought is to cross multiply and get e to the 7 times e to the 6k equal to 13 times e to the 2k. Although really it's kind of jumping the gun because I really want to bring all the k's to one side. So what I should really do now is divide both sides by e to the 2k. So I probably didn't need to actually cross multiply. It's all right. So now I have 7 times, what's e to the 6k divided by e to the 2k? Right, because we're just subtracting those powers. So 7 times e to the 4k equal to 13. I guess we should also divide both sides by 7 and get e to the 4k equal to 13 over 7, which means the natural log of e to the 4k is going to equal the natural log of 13/7. So we end up getting 4k equal to the natural log of 13/7. And finally, k equal to 1/4 times the natural log of 13/7. All right. So then to figure out what C is, you can go back to either one of these equations. It's going to look a little different depending on which one you pick, but they're both going to be the same. So if I plug it into the first equation, I'm going to get C equal to 7 over e to the 2 times 1/4 times natural log of 13/7, which looks pretty terrible. We probably would, yeah. I kind of want to simplify this just to show you how this simplifies, because there is some simplification that can be done here. It's not particularly nice, but it is a little bit nicer. So let me show you what I mean. This is going to be 7 over e to the 2 times 1/4 is 1/2 natural log of 13/7. And then, and here's where things get a little spicy. 1/2 times natural log of 13/7, that 1/2 can come up as the power of 13/7. So I can rewrite that as 7 over e to the natural log of 13/7 to the 1/2 power. But then e to the natural log of some stuff is just the stuff. So what we really have here is 7 over 13/7 to the 1/2 power, which is weird, but fine. I might rewrite this as 7 times 7 over 13 to the 1/2 power. Or if I really want to simplify it as much as possible, 7 to the first times 7 to the 1/2 is 7 to the 3/2 over 13 to the 1/2. It's not pretty. Yeah.
Where did e squared come from first?
Say it one more time.
Where did e squared come from?
Sure. I'm using this part right here. And I'm saying, okay, now I'm going to actually plug in the value I found for k. So I'm taking that and then putting that in for k here. And then I'm getting 7 over e to the 2 times k. Now, if you're doing this in web work, all this simplification I've done here is really unnecessary, right? If you're doing this in web work, you should really just type this in, because doing simplification is really just an opportunity to get it wrong. So I would, if you're doing this homework, I would encourage you just to kind of leave it as is. When you cross multiplied, how did you get e to the 2k as the denominator for both? So when I cross multiplied, I first had this, but then I realized I was trying to solve for k. So I said, oh, I want to get all the k's on one side. So I divided both sides by e to the 2k. And so really in actuality, the first step I could have done if I was trying to, do less steps here is I could have started with 7 over e to the 2k equal to 13 over e to the 6k. And what my first step, sorry, you can't really see that. Well, my first step could have been to do less steps, would have been just multiply both sides by e to the 6k. And also divide both sides by 7. Then on the left side, the 7's cancel. And on the right side, the e to the 6k's cancel. And you're left with e to the 6k over e to the 2k equal to 13 over 7. Sometimes I get a little carried away. I'm like, oh, let's just cross multiply because that feels like an easy thing to do. But if I was trying to do less steps, I could have been like, oh, I really need all my k's on one side, so I should do that instead. Let's look at one or two more. I definitely had an example here that I wanted to do. Let's see here. Oh, yeah, that's a good one. We'll look at one or two more. This next kind of question I feel like is always interesting. So after 3 years, 80% of the initial amount of a radioactive substance has, so what do I want to use here? Has decayed. What is the half-life of the substance? Not very informative. They're not giving me a lot to work with here. So typically, although not always, but typically, if you're given a problem like this and you're told we're starting with some initial amount and then later on we have some percentage of it, you can make up whatever amount you want to be your initial amount. And I'm going to make the easy choice in that I'm going to say that at time equals 0, my initial amount is going to be 100. 100 is really easy to work with when talking percentages. You could say 100 grams, you could say 100 pounds, you could say anything you want. I'm going to say 100 grams because that's kind of the typical choice. And then I know that 3 years later, how much radioactive substance do I still have? Well, we have to be careful about reading the question. Right? This question specifically says, 3 years later, 80% of the initial amount of radioactive substance has decayed, meaning that is not what's left. That's what's gone, and the other 20% is still remains. So after 3 years, we have 20 grams remaining. And now our job is to find the half-life. So our job is to find what time is it when we have half the amount that we started with. So as we just kind of did, yes, 20 grams. We're going to use these two data points to find C and K in our model. And then after we find C and K and we have the brand new model, we can use this last part to figure out what time it is when there's half the amount of stuff, or to find the half-life, in other words. So similar process. I should really point this out because it's worth pointing out. So there is a way of doing this where you don't have to work quite so hard to get the C and the K value. C is not terrible. C is 100 here. I can see, not really, but that I'm going to have something like this. Y equals 100 e to the kt. And we can find K. And sometimes we really want to find K. Like, right, definitely in these problems, you're being asked to find K a lot of the time. But I really feel compelled to mention there is kind of a faster way to get to where you want to be if you just need the model. And that's the following. I can say that Y equals 100 times Okay, so let me ask you, after 3 years, what fraction do I have of what I started with? A fifth. Now, I don't even have, you guys did the extra work and reduced that fraction. I'm going to say I had 20 hundredths, but you're right, it's a fifth. So I have 20 hundredths of what I started with. And it took me 3 years. So I'm going to say that's going to be raised to the t/3 power. Now let's look at this and see if it works. If I plug in 0, do I get what I want? Well, let's see, 0 divided by 3 is 0, and anything to the 0th power is 1. So yeah, when I plug in 0, I definitely get y equal to 100 times 1, which is 100. And when I plug in 3, do I get what I need? I do. So when I plug in 3, I get y equal to 100 times 20 over 100 to the 3/3 power. 3/3 is 1. Anything to the first power is itself. So 100 times 20 over 100 is just 20. So this is a faster way of getting to the exponential equation that is the model for growth or decay. Now, this doesn't look the same as the other way we're going to see it, but it actually is the same. And I want to point that out to you. I should say, this is usually discussed less in the 16 series specifically, because it's just not the way we usually do it. Whereas in other, like definitely in the 17 series, I know it doesn't really matter, but in the 17 series, they kind of talk about it a different way because there's kind of biological applications for that. But it's kind of nice to see that there is this faster-ish way of doing it. Now, if we were going to do it the other way, where we say, well, we have y equal to 100 e to the kt, and we plug in our t and our y value, let's see what happens. So 20 equals 100 e to the k times 3. Solve for k. 20 divided by 100 is 20 divided by 100. It's equal to e to the 3k. And then we're going to take the natural log of both sides. So the natural log of 20 over 100, I guess I could reduce that to 1/5, is equal to 3k. So k is equal to 1/3 natural log of 1/5. And then plugging that back in to write our model is going to be y equal to c e to the k t. And what I really kind of feel like I need to say here is that these are the same. I know they don't look super the same, but they are. Let's see that. I feel like that's worth seeing. So let me do it this way so you can see the things. So I'm going to start with this one. I've got 100. Let me write a little bigger. I feel like I write too small sometimes. So here's the trick. First of all, we're going to rewrite this as 100 e to the t times 1/3 is t over 3 times the natural log of 1/5. And then this t over 3 gets to become the power on the 1/5 there. So this is really 100 e to the natural log of 1/5 to the t over 3. And then I think we can see it. E to the natural log of whatever is just the whatever. So this is 100 times 1/5 to the t over 3. But that's exactly what we have up there. 100 times 1/5 to the t over 3. They're totally the same. It's kind of cool. So there is a quote unquote maybe faster way of getting there. If you know that it takes so long to have some fraction of what you started with, those are the numbers you use. There's the fraction, beginning thing, next thing. There's your time divided by how long it took. It's kind of neat. Anyway, back, oops. So, sorry, brain. We want to find the half-life. So we're going to plug in y equal to 100 and solve for t. So let's see. Let's see here. So plugging in y equal to 100. Really? You guys let me get away with that? What am I really plugging in? I didn't mean to do that, but like, yeah. if you see something that seems like it might be a mistake, especially if I'm distracted because my phone is ringing because my godson is calling me, I need to call him back. Let me know, right? If you think like, James, it seems kind of wrong, you're probably not wrong. So 50 is what we're setting y equal to. And that's going to be 100 e to the 1/3 natural log of 150. And then we divide by 100, so we get 1/2 equal to e to the 1/3 natural log of 1/5 t. Then we take the natural log of both sides. So I'm not going to write it out this time. We've taken the natural log of e to the something enough times to be like, okay, we know when we take the natural log of e to the something, we just get the something. Right? He said he's not going to write it. That's the natural log of e to the 1/3. And then we're going to solve for t by dividing by all this. So no, that's fine. So t is going to equal natural log of 1/2 divided by 1/3 natural log of 1/5. And the only thing I would say about this is I don't love having a fraction in the denominator there, so I would probably rewrite this as t equal to 3 natural log of 1/2. And that's our half-life. Now, it doesn't feel very meaningful written that way. Like, I mean, okay, I don't know what that number is. So that's the answer we should give. But if we actually wanted to approximate that, we need to calculator, which I definitely brought a calculator because I planned ahead. So if we actually want to figure out what that is, we're going to do 3 times the natural log of 1/2 divided by the natural log of 1/5. Okay, so it's about 1.3 years, which seems reasonable, right? If it took 3 years for it to decay to 20%, it should definitely take less time to decay to 50%. It's good to think about if your answers make sense contextually, right? If it takes so much time for something to happen, you should be thinking, okay, well, compared to that amount of time, should it be more or less? Yeah.
Why did you get that? Like the LN? We could just use the properties.
So one more time.
Like what do you have to like add that?
From this step to this step.
Yeah.
So I'm trying to solve for t. There's not a good way of getting t or variables in general out of the exponent without taking a logarithm of both sides. I guess my question would be, how else could we do it? And I don't have a good answer. I don't think there is. I don't believe there is a good answer other than, right, when we're trying to solve something with a variable in the exponent up there, we kind of have to take the natural log of both sides, or any log base you want, but typically the log base e, the natural log, is the usual choice. Good. Yeah, that feels like a sufficient amount of talking about exponential. Yeah. I was waiting for someone to ask that. That's a good question. I mean, the answer should be yes, but let's see. So if instead we have, so our other equation was, I forgot what it was. It was 100 times, what was it? 1/5 to the t over 3. Right, that was our other equation. Yeah. So let's see. Well, same idea, right? We still are trying to solve for t. So we're still going to first isolate the thing that's being raised to an exponent. So I still need to divide both sides by 100. And so then I have 1/2 equal to 1/5 to the t over 3. And then to get that variable out of the exponent, what do I need to do to both sides of this equation? Take the, yeah. And really you could use any log base. Like technically you could use log base 1/5 if you wanted to, but the natural log is the one we typically choose. 1, because it's less writing. 2, because it's the button that's easily accessible on your calculator. Those are kind of my best reasons. Okay, so then the t over 3 gets to come down in front. So we have natural log of 1/2 equals t over 3 times the natural log of 1/5. And then, oh, solving for t, I'm going to multiply both sides by 3 and divide both sides by natural log of 1/5. So yeah, we get exactly the same answer. You might feel like it was easier to do it this way. I kind of feel like it was easier to do it this way. But what I'll point out is that certainly some of the questions on these homework assignments specifically ask you to find C and K. And you don't get C and K doing it this way. So you can't necessarily just do it this way and answer the questions that they might ask you. But yeah, it's kind of, so just as kind of a, just to see, no, we shouldn't spend, I want to say more about it, but we really don't need to spend more time talking about it. But let's look at, there was one other thing I wanted to kind of mention just before we keep going here. Let's say I had f of x equal to 6 to the x, and I want to find second derivative. So whenever we're finding a second derivative, you have to first find the first derivative. So I know it's been a little while since we've seen each other. What's the derivative of 6 to the x? 6 to the x times something is 6 to the x times the natural log of 6. I know we talked about this maybe like a week ago. So, right, it's easy to forget things. But whenever you're taking the derivative of some base to the x, you just get that base to the x times the natural log of that base. If that base is a constant. And then if we want to find the second derivative, you take the, well, this is a constant, so it's just going to hang out. So you're going to get the derivative of this, which is 6 to the x times natural log of 6 times another natural log of 6. That's it. And then I just remember that I saw something that somebody's teacher did that was fine, but it's not the way I would do it. So let's actually go explore one more thing, and then we'll talk about or antiderivatives. Come back, paper. Okay, so let's say we wanted to find the derivative of, sure, let's say y equal to 9x to the 2x squared power, where both your base and your exponent have a variable. And we definitely have seen examples like this before, but I want to point out that one class, I don't remember which one, actually derived a formula for something like this. I saw it in the notes. It looks heinous. It is terrible, right? Like you have f of x to the g of x, and the derivative of that, it's like the derivative is f of x to the g of x times, I don't know, like f prime natural log of g plus bizarre. You don't want to do it that way. There's no good reason to memorize that formula unless your teacher specifically has demanded that you do it. They shouldn't. It's a terrible formula. The way that you should find the derivative of something like this is by using the process that we've talked about before called logarithmic differentiation. So the way we want to find this is, I mean, okay, that's not the only way. It's the way okay, fine. There's two ways of doing that are fine. The way I like to do it is by taking the natural log of both sides. And then bringing down this 2x squared. So I have 2x squared times the natural log of 9x. And then differentiating both sides. So 1 over y times y prime, right? Because the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then on the right hand side, we're going to use the product rule. So the derivative of 2x squared is 4x times the natural log of 9x plus 2x squared times the derivative of the natural log of 9x is 1 over 9x times 9. Just as a reminder. It's product rule. And then you can, I kind of like to do the last two steps in one. So here's the final result, and I'll go back and show you the intermediate step if you want. I'm going to get y prime equal to y, which is 9x to the 2x squared times all this stuff. 4x times natural log of 9x plus, I can do a little simplifying here. I can cancel a 9 and an x and just get 2x. But the intermediate step, if you want to write it, would be writing y prime equal to y times 4x natural log of 9x plus 9 times 2 is 18x squared over 9x. And then replacing y with what it's actually equal to and simplifying this as 2x. This is one way of doing this problem. I guess there are technically two other viable ways of doing it. One is the not excellent way of memorizing the formula. I really can't stress enough how much I don't recommend that. It's a terrible, terrible formula. It's also just, I mean, I'm not good at memorizing things. Maybe you're really great at memorizing things. If you're good at memorizing and you want to memorize it, that's the way you should do it. But I personally can't recommend it. The other way of doing this I can recommend is, and let's do a slightly different problem just for fun, is, well, it's kind of blurry there. Okay, there we go. What's your problem? There used to be like a, oh, there we go. Okay. So let's say we want to find the derivative of something like y equal to, let's make it a little more fun, 2x plus 3 to the 5x cubed power. So one way of doing it is the way we did it before, where we took the natural log of both sides and so on and so on. The other way we can do this is by rewriting the right-hand side as e to the natural log of the thing. So we can write it as y equal to e to the natural log of all of that stuff. We're still using the same special tool in that when you have the natural log of something to a power, that power gets to come down in front of the natural log. So really all of this is resting on the fact that we can do this thing. This is going to be e to the 5x cubed times the natural log of 2x plus 3. So in the same sort of way, right? So our first step is this. Our second step is to use that same sort of idea, where we're bringing down the power in front. We're bringing down the power in front. Okay. When we take the derivative of e to the stuff, we're going to get e to the same stuff. And then we have to multiply by the derivative of the stuff, which is going to require the product rule, just like it does in the other way of doing it. So product rule, we're going to get the derivative of 5x cubed times the natural log of 2x plus 3 plus 5x cubed times the derivative of the natural log of 2x plus 3, which is 1 over 2x plus 3 times 2. And sorry, I'm a little off screen there for the people on Zoom. Apologies. We go out. But really, it's the same. It's really the same steps either way you do it. They just kind of look a little different. The one reason I like this method a little bit less, it's probably this last part here. When I'm simplifying this, I really do need to remember or see that this part here is the original function you started with. This is your 2x plus 3 to the 5x cubed. It's just written differently. But it is, right? Because the way we got this was by bringing down the power. So, right, this is the same as that, and that's the same as that. But when you're writing the answer, there is kind of this expectation that this original expression shows back up as it's originally written. So we really have 2x plus 3 to the 5x cubed times all this stuff over here, which I would simplify minimally as 5x cubed times 2 is 10x cubed over 2x plus 3. Either way of doing it's fine. I really, really would do it one of these two ways. Okay. So let's see, what's that, yeah. So I'm pretty sure Burke's class started talking about antiderivatives, but the other class hasn't yet. Okay. Well, you're going to talk about every class is going to talk about it eventually. So it's definitely good that we start talking about them. And I know we did a little bit last week. Let's continue. Oh yeah, that's definitely. I was trying to remember what I want to talk about. So antiderivatives. What to say? Really, really important to understand that you are undoing a derivative. So when someone says find the antiderivative, we really want to be thinking, I'm looking for a function that if I take its derivative, I get the thing I started with. So if I'm trying to find the antiderivative of 6x squared plus 8x plus cosine of x, I'm looking for the function whose derivative is equal to all of that. So I'm looking for something whose derivative is 6x squared. Well, let's see, I think that's going to be 6x cubed divided by 3. Because when I take the derivative of 6x cubed, I'm going to get 18x squared, but then I don't want 18, I want 6, so I need to divide by 3. When I take the antiderivative of 8x, I need to get 8x to a 1 higher power divided by that new power. We're going to check in a minute, but this is the thought process for the what I like to call the anti-power rule. If you have x to a power, the antiderivative, you're going to add 1 to the power and divide by the new power instead of multiplying by the power and subtracting 1 from the power. Right? You're literally doing the opposite things of the derivative in the opposite order. And then finally, okay, so it's really important. We have to distinguish between the derivative and the antiderivative. What is the derivative of cosine of x? Negative sign. And the way I always remember the derivatives of the trig functions, or specifically what if they're positive or negative, is all of the co-functions, cosine, cotangent, cosecant, all of those have negative derivatives. And the other 3, sine, secant, and tangent, have positive derivatives. So now I'm looking for the antiderivative of cosine. I want to find the function whose derivative is equal to cosine of x, which is sine of x. And then we tack on a constant because the derivative of a constant is just 0. I'm going to simplify this a little bit. It equals 2x cubed plus 4x squared plus sine of x plus c. And now I'm going to check my work. So let's check. Is this right? Well, what's the derivative of what I just found? The derivative of 2x cubed plus 4x squared plus sine of x plus c is going to be, let's see, the derivative of 2x cubed is 6x squared. The derivative of 4x squared is 2 times 4 is 8x to the first. The derivative of sine of x is cosine of x. The derivative of constant is 0. Oh yeah, those match. That means we did it right? This is the antiderivative of that. So its derivative should be what we started with. So if the antiderivative of a function is some other function, then the derivative of that antiderivative should equal the original function. It's a really, I know I've said this last time too. I can't stress it enough how important this relationship is. That if you are finding the antiderivative of something and getting an answer, the derivative of that answer should get you back to the function you started with. Antidifferentiation and differentiation are processes that undo each other every single time. I will say there is one kind of, I say that and there's like a small little caveat. So if you start with a function and do the derivative and then do the antiderivative, you don't exactly get back what you started with. Here's what I mean. Let's say I started with capital F of X equal to, I don't know, let's pick something fun, exciting, like x to the fourth plus tangent of X. Okay, the derivative, hopefully everyone can see that, yeah, which I'm going to call little f of X is going to be, let's see, the derivative of x to the fourth is 4x cubed, and the derivative tangent is secant squared of X. And then if you do the antiderivative of that, you don't exactly get back what you started with because you have to tack on a plus c. So I would say that the antiderivative of little f of X here, which is the antiderivative of 4x cubed plus secant squared of X, is technically going to be x to the fourth plus tangent of X plus a constant. So it's not like exactly the same, but it's the same, right? That's not a big, excuse me, it's not a big enough difference to say they're different. Okay, so let's go in here. The first method of integration, so I should back up a little bit. One thing you're going to do if you're antidifferentiating is first we're going to try to simplify the function as much as possible. So if you can write the thing you're antidifferentiating as just powers of your variable, that's great. That's really kind of ideal because then we can use the anti-power rule to antidifferentiate it. So for example, if I was trying to find the antiderivative of t to the fourth plus 5t cubed times t to the seventh minus 2t squared, the only real option here is to multiply it out to get powers of my variable. So if I multiply this out, I'm going to get t to the fourth times t to the seventh is t to the 11th. T to the fourth times negative 2t squared is minus 2t to the sixth. 5t cubed times t to the seventh is 5t to the 10th. And 5t cubed times negative 2t squared is minus 10t to the fifth. I probably could have written that in a slightly more standard order. Oh well. And now each of these things we're going to antidifferentiate using the reverse power rule, where you add 1 to the power and divide by the new power. So we're going to get t to the 12th over 12 minus 2 times t to the 7th over 7 minus 5 times t to the 11th over 11 minus 10 times t to the 6th over 6 plus a constant. That's it. That's our answer. We're done. That's the antiderivative of that function. Something to say there. Maybe not. There's something in my brain. Now it's disappeared. Question? Yeah. Because yeah, that's a good question because I saw an X pretend negative sign. There should be plus. Yeah. Unless yeah. I know what I wanted to say. So I feel like I might have said this before, but when you antidifferentiate something, once you actually find the antiderivative, you no longer want or need to write the integral symbol or the differential here. So what I like to point out is this thing here and this thing here. Those are just instructions telling us to antidifferentiate. And once we have done so, they go away. The reason I mention this is because I see a lot of people sometimes just keep writing the integral symbol even after they have taken the antiderivative. So once you've taken the antiderivative, you really, really don't want to write that symbol anymore. Let's look at, yeah, so the problem is I'm trying not to go too far ahead, but like want to prepare you for what's coming. Let's look at another. Why don't you all try doing this one? So try finding the antiderivative of x to the sixth plus 2 over x to the sixth minus square root of x. And it's definitely going to be necessary to rewrite all those things as powers of x. I'll give you a minute. People at home on Zoom, you should also do this problem. Or if you're watching the video later, stop, do the problem. So we should rewrite this as the integral of x to the sixth plus 2x to the negative sixth minus x to the 1/2. This pen is less than ideal. And this is, each of these are just powers of x. We're going to use the anti-power rule. Okay. X to the 7th over 7 plus 2x to the negative, nope, not negative 6, negative 6 plus 1 over negative 6 plus 1. Do be careful when the powers are negative, right? When you add to a negative power, it becomes less negative. And then we have minus x to the 1/2 plus 1 over 1/2 plus 1. Now I'm going to simplify that a little bit. You can write x to the 7th over 7, or some people prefer to write 1/7 times x to the 7. Either way is totally fine. Here I am going to write this as minus 2/5 instead of 2 over negative 5 times x to the negative 5. And then here I'm going to have minus, I'm dividing by 1/2 plus 1, which is 3/2. But instead of dividing by 3/2, I'm going to write multiplied by 2/3. And then my power is going to be x to the 3/2. That's how we would do a problem like that. So definitely the reverse power rule is something you want to get very familiar with. It's going to come up all the time when you're doing antiderivatives. But it's pretty, I mean, just like the power rule, it's kind of very, I don't know what the right word is here. It's very much the same thing every time. You're just doing the same thing every time, all the time. It's just add 1 to the power, divide by the new power. I do think it's worth practicing though, because so let me have you all do another one. I'm going to make it a little bit harder. Let's try, I want you all to try this one. Let's say we have x to the 6th plus the cube root of x minus 1 over x to the 4th. So I want you to try to find the antiderivative of that. And you're definitely going to need to simplify the integrand, the stuff you're antidifferentiating, before you find the antiderivative. rule. So a couple things. First thing I wrote over here just to kind of make sure everyone is aware, we can't just take the antiderivative of each piece and then put it all in some fraction. So we definitely, it's not x to the 7th over 7 plus x to the 1/3 plus 1 over 1/3 plus 1 minus x over x to the 5th over 5, right? That's definitely not going to work for us at all. Because if it did, we'd have to take the derivative of this and get that. But if we take the derivative of this, we'd have to use the quotient rule, and we definitely wouldn't get that. So there's no like anti-quotient rule, unfortunately. We have to kind of just simplify. So simplifying this, I'm dividing each of the things in the numerator by the denominator, and then rewriting it as, let's see, x to the 6th divided by x to the 4th is x squared. X to the 1/3 divided by x to the 4th. Okay, 1/3 minus 4 is 1/3 minus 12/3, which is negative 11/3. And then we have x to the negative 4th. So all I've done so far is simplify. So I keep writing my symbol saying I need to integrate, and now I'm actually going to integrate or antidifferentiate. We're going to get x to the 3rd over 3. I'm going to end up getting a negative coefficient here because I'm going to dividing by something that's negative. So I'm going to have minus, or what's my new power going to be? If I add 1 to negative 11/3, it's going to be 11/3 plus 3/3 is negative 8/3. So I'm going to have x to the negative 8/3. And then instead of dividing by negative 8/3, we're going to multiply by negative 3/8. That's a pretty common move where you say, okay, my new power is this. Instead of dividing by that new fractional power, we multiply by that new fractional power as reciprocal. And then we're going to have, I know it's going to be plus, right? Because I'm going to get minus x to the negative 3rd divided by negative 3. And I don't want to write it again. So I'm going to write plus x to the negative 3rd divided by 3. So it's really minus x to the negative 3rd divided by negative 3. All right. What time is it? Okay. So here's where I really want to get you to. I want to talk about a process called u-Substitution, which is kind of the first thing you learn to do after you learn how to simplify things. So u-Substitution. U-Substitution. Wow, can I spell u-Substitution? Yeah, there's a lot of T's in there. Okay. Is a method for integration, which allows us to take things that are complicated and make them less complicated. Let's look at an example. Let's say, let's see where I actually grab my notes here. So I've got examples that are just all over the place. So let's make it semi-straightforward here. So I want to find the derivative of 7x to the 6th times x to the 7th plus 3. One way of doing this problem would be just to multiply it out. Totally work just fine. So we're going to do that so that we can see that doing this other process also works. So multiplying it out, let's see, 7x to the 6th times x to the 7th is going to be 7x to the 13th. And 7x to the 6th times 3 is going to be 21x to the 6th. When I antidifferentiate that, I'm going to get 7x to the 14th over 14 plus 21x to the 7th over 7. Let's see, and then simplifying a tiny bit, I get x to the 14th over 2 plus 3x to the 7th. Let's see. Great. You can stop me if you have questions or chime in or say something. So here's another way of doing a problem like this. So for this integral, we are going to pick something to be u. Really what we're picking, how do I say this the right way? What we're really picking is the inside part of the chain rule. So u-substitution is kind of like literally undoing the chain rule. So we're trying to find essentially the stuff, right? When you take the chain rule, like if you're doing like the derivative of a function of some stuff, the derivative is the derivative of the outside part, leave the inside stuff alone, and then multiply by the derivative of the stuff. We're looking for the stuff whose derivative is also there. So in this particular problem, I'm going to let u equal x to the 7th plus 3. That's the stuff. With the hope or the observation that the derivative of that stuff is also in my integral. It is. What's the derivative of x to the 7th? 7x to the 6th. And that is definitely in there. So now what we typically do is we isolate du. We rewrite this as du equal to 7x to the 6th times dx. And we're actually going to change this integral, this antiderivative, from an antiderivative of things with x's to an antiderivative of things with u's. I like to think of it as a translation problem. We have to translate it completely from the language of x to the language of u. You can't have x's and u's. You either have to have just x's or just u's. So we're going to change it all to u's. And I'm going to rewrite it to make it a little easier. I have x to the 7th plus 3 times 7x to the 6th dx. I just changed the order of multiplication. And then I'm going to observe that this here is equal to my du. It's vital when we do a u-substitution to make sure that the dx turns into the du thing first. Everything else after, dx has to change into du. Because the dx or the du is telling you what variable to antidifferentiate. So this is saying, oh, antidifferentiate the variable x. This is going to say antidifferentiate the variable u. And then this part here, that's just what we chose for u. So now we're going to have this integral transformed into the integral or antiderivative of u du, which you might think of as u to the first. Just to make it a little more obvious what's going to happen. What's the antiderivative of u to the first? U to the, yeah, divided by 2, plus a constant. Okay, but now, whenever you're doing a u-substitution and it's an indefinite integral where you're just finding the antiderivative, right? There aren't, I know we haven't talked about like area under a curve, area and that stuff, but like this integral doesn't have any limits of integration. There's no lower thing here or upper thing here. We're just getting an answer that's a function. If we're getting an answer that's a function, it needs to have the same variable that we started with. So if we started with x's, we need to end with x's. So we need to replace u with what it's equal to. And u was x to the 7th plus 3. So replace. Are these answers the same? Here for 16C?
No.
Oh, well, that's what's going on right now.
Thank you so much.
You're welcome. So, are these the same? Well, let's find out. So when you square something, you get the first thing squared to x to the 7th squared plus 2 times the first thing times the second thing plus the second thing squared all over 2. So simplifying this, x to the 7th squared is x to the 14th over 2. 2 times x to the 7th times 3 is going to be 6x to the 7th over 2. And then I've got a 9 over 2. So it's almost the same. It's x to the 14th over 2 plus 3x to the 7th plus 9 halves plus a constant. So they're not quite the same, but they're close enough. Because these answers, well, really, oh, I'm sorry, you can't see. Thanks. Sorry. So these answers here, these constants aren't necessarily the same. But this and this match up. So as long as your answers differ by no more than a constant, they're technically, for all of our purposes, the same thing. So the takeaway here is that this process works, right? We took the derivative of this and we took the antiderivative and got the same thing. And really, the reason this is working is because of the chain rule. So let me just point out that if we look at this version of it, so where our antiderivative of x to the 7th plus 3 times 7x to the 6th dx is equal to x to the 7th plus 3 squared over 2 plus c. The derivative of that, which I'm going to write as 1/2 times x to the 7th plus 3 squared. When I take the derivative of some stuff squared, I'm going to get 2 times my stuff to the first power. And then what do I have to multiply by? The derivative of the stuff. So that's why we are looking for this to be our choice for u here, because its derivative is showing up in the integral. We're actually undoing the chain rule. Let's look at another example, a slightly more complicated example. Well, not a ton more complicated. So let's say we had something like this. The integral of 4x cubed times x to the 4th plus 1 to the 99th power. In this case, technically someone could multiply it out. It would take a while. You don't want to do that. So really, we are kind of forced to do a u-substitution here. So what are we going to pick for u? What seems like a good choice? Let's talk about why this is a good choice. So there are 2 things to look for when you're picking u. When you're picking u, you want to pick a u whose derivative is also in the integral. Well, great, we did it. We picked a u, and the derivative of that is 4x cubed, which is in the integral. Now, really, I'll tell you, you don't have to have the right coefficient, right? Like if this had just been x cubed here instead of 4x cubed, this would still be a great choice because we can figure out how to adjust for a constant multiple. The other thing, so I will say, this is what you want. You want to pick u so that the derivative of u is also in your integral. Typically, one way to identify a plausibly good choice is to look for something that is stuck. That's the word I like to say, right? Inside another function. In this particular problem, that x to the 4th plus 1 is stuck in the function of being raised to the 99th power, right? You can't get it out of there. It is really kind of just, it's stuck. There's no way to deal with it. Some other examples would be, and I'm going to use the same choice of u and du here. would be something like the integral of 4x cubed times the square root of x to the fourth plus 1. There's no way of getting the x to the fourth plus 1 out of the square root. Or the integral of 4x cubed times cosine of x to the fourth plus 1. Or even the integral of 4x cubed over x to the fourth plus 1. Each of these are examples of where your choice for u being x to the fourth plus 1, we're choosing it for both of the good reasons. We're seeing that x to the fourth plus 1 in each of these integrals or antiderivatives is stuck inside another function. This one is stuck inside a square root. This one's stuck inside a cosine. This one's stuck inside the denominator. If you like, you could rewrite this one as 4x cubed times x to the fourth plus 1 to the negative first power. Seeing that it's stuck being raised to some power. And then its derivative is also in the integral, which is really the most important part. You don't have to have your piece being stuck. Like, in fact, in the first example we did, this x to the 7th plus 3 isn't really stuck, right? We totally multiplied it out and did it the long way. But it's usually a good way of thinking, oh, that thing that's stuck there, that's probably a good choice for you. I'm going to try that because it seems like a good choice. And then maybe it doesn't work and you try something else. There are some examples we'll see later on where the thing that looks like it might be the best choice for you doesn't work out and you have to try something else. But it's usually a good way of starting. Be like, well, I think that's where I want to start. And then we're going to rewrite our integral. So we're going to say, all right, the integral, and I do like to write it. So people do this various ways. I personally am a fan of isolating du and saying du equals 4x cubed dx, and then making this thing show up in my integral. In this case, it's already there, right? I have exactly those two things together multiply to du. I don't have to do any extra work. In the next example, we'll see we have to do a little extra work. So I'm going to rewrite this integral as x to the fourth plus 1 to the 99th power times 4x cubed dx. There's my du. There's my u. And then this is going to become the integral of u to the 99th power du. And the point of this is it's supposed to get easier, right? This new thing, we should be able to antidifferentiate often with just the power rule, or sometimes a trig function thing. So this is going to end up being u to the 100th over 100 plus c. And then we have to plug back in what u is equal to. So plug in u equal to x to the fourth plus 1, and we're going to get x to the fourth plus 1 to the 100th power over 100 plus c. And you'll notice that if we took the derivative of this, we essentially have some stuff to the 100th power. And the derivative is 100 times our stuff to the 99 times the derivative of the stuff. But what I really want you to see here is that when you take the derivative of, I'm going to write it this way, you're going to get 1 over 100 times your stuff to the 99th power times the derivative of your stuff. The thing I'm trying to point out, and I'm kind of taking a while to get there, is that the stuff in your chain rule derivative is the thing that should be the u, right? You're trying to find the u so that the derivative of u comes up. Because if you took the derivative of this using the chain rule, you're exactly going to get the stuff with some power times the derivative of the stuff. So that's why we're choosing u in this way, where we're hopeful that its derivative is also in there. Okay, we got time. We got time for one more. So we're going to do another one. It's going to be, we'll find. Talk about that next time. I was hoping I would get a chance to talk about what I like to call mini u-substitutions, which are the ones that should be like kind of fast and easy, but we're going to get there. So let's look at one more example. Let's say it's the integral of x to the 5th times the square root of x to the 6th plus 9. Okay, so from all the stuff we just said, what seems like, what should be the thing I should probably pick for you? What seems like a maybe good choice? Yeah, x to the 6 plus 9. I feel like I maybe heard someone say the square root. I don't actually want the square root part. I just want the stuff inside the square root. So I want the thing that's stuck, because I typically want to make a choice for you whose derivative is pretty easy. And if I have the square root of all that, then it's going to get a little complicated. Now, sometimes you do want to pick the square root part, but for now, we don't. That is a dx, not a 2x. So then my derivative, what's the derivative of x to the 6 plus 9? And I don't exactly have that, but I don't care. Meaning I do care, but I can fix it. I don't care if I'm off by a constant multiple. What I care about is that the x to the 5th here is matching the x to the 5th there. That 6 is a problem we can easily deal with. So this is where there's a number of ways of doing it. I like to do the following. I like to make this part here look like what I have in my integral, meaning I don't have a 6. So I like to say I'm going to multiply both sides by 1/6. So that 1/6 times du equals x to the 5th times dx. That is my preferred way of doing it. So I'm going to rewrite this as, and I really do like reordering things so that the part that's my du kind of fits together. Again, it's not necessary. It's probably a waste of time. But I like to say, okay, that's my 1/6 du. It is super duper vital that the dx part changes into the du part. We have to make sure that happens. Otherwise, it's not going to be right. This is going to equal the integral of something times 1/6 du. And it's going to be the square root of u times 1/6 du. I personally, and I think not just personally, this we should really pull out in front. Constant multiples in integrals, it's usually a good idea to just bring them out to the front of the integral. And then the square root of u, I'm going to rewrite as u to the 1/2. So then use the anti-power rule, you're going to get 1/6 times. The antiderivative of u to the 1/2 is u to the 3/2, and dividing by 3/2 is the same as multiplying by 2/3. Plus c. And then we should simplify and change it back into x. So 1/6 times 2/3 is 2/18, which is 1/9. And then u, I'm going to replace with what it's equal to. So I'm going to have x to the 6 plus 9 to the 3/2 power. And that's our final answer. And if we look at this, if we take the derivative of this, you're going to, the 3/2 is going to come down. You're going to get x to 6 plus 9 to the 1/2 power. And then you would end up multiplying by the derivative of the inside, which is 6x to the 5th, which is where that x to the 5th is going to come from. One note, alternatively, some people, instead of doing this like I've done here, some people prefer to do a thing where they say, oh, I've got du equals 6x to the 5th dx. And I really would like there to be a 6x to the 5th dx in my integral. So what I'm going to do is I'm going to take my integral and, well, I wish there was a 6 there. I can't just multiply by 6. If I multiply by 6, what else do I have to multiply by? 1/6. Or I should say, if I multiply by 6, what else do I have to divide by? Also 6. So that I only multiply by 1. So now this 6x to the 5th dx becomes my du, and the square root of x to the 6 plus 9 becomes u. So this still is going to be the same thing. It's just a slightly different way of getting there. I will point out you can only really do this thing where you say, what do I want to have there? And then do 1 over it out there. If the thing you want to have there is a constant. You can't like throw in an e to the x and then divide by e to the x on the outside of the integral. That's a giant problem that we can't do. But if you're just trying to adjust by a constant, totally fine to multiply inside the integral by the constant and divide outside by the integral by the same constant. I like this less than this, but they're really the same thing, just doing it a different way. And then, no, I should stop. It's 10:21. I should stop talking. There are other ways of doing this. Some people, so I stopped. I should stop talking. He keeps talking. Some people like to solve for dx here completely and then plug that in. I don't like that, but it also works usually just fine. We'll talk more about this on Thursday. And on Thursday, we'll also talk about mini u-substitutions, which are u-substitutions that you want to essentially be able to do without actually writing out because they're pretty small. Okay, that's all. I'm really going to stop talking now. Have a lovely, lovely rest of your day.